consider a set of ordered pairs. Here's an example of a set of ordered pairs here. While this one's finite, we have a total of 5 ordered pairs. These could also be infinite. A relation is any set of ordered pairs, such as this one. The domain of a function is the set of all of the first components of the ordered pairs. For this particular relation, that would include 1, 2, 6, 2, and 3. To write this, we would use curly braces and list out 1, 2, 3, and 6. Even though the 2 appears twice, we should still only list it once. The set of all the second components of the ordered pairs is known as the range. The set of all second components of the ordered pairs is known as the range. For this particular one, we have 5, 6, 3, 5, and 0. We would once again write this between curly braces, and this would be 0, 3, 5, 6. Just like with the domain, we do not need to repeat the 5, even though it appears twice. All of the individual values in a domain are known as the input. So the domain is the entire set, but the input are each individual values. These are often denoted by the letter X. The values in the range are known as the output values. So the individual values in the range are the outputs, and the range is the entire set. And these values are often denoted with the letter Y. While relations are important, we really want to restrict this to a special type of relation known as a function. A function is any relation in which each input corresponds to exactly one output. This means that we don't want to repeat input variables. As an example, if I look at this relation here, I can see that the 2 occurs twice as my input values, so that tells me that this is not, in fact, a function. On the other hand, if I look at this relation here, I can see that my input values are 1, 2, 3, 4, and 5, which are all different, which means this set of ordered pairs is a function. Ordered pairs are only one way to represent a function. Another way to represent relations and functions is with what's known as an arrow diagram. In this case, all of the inputs or the domain is listed on the left, all of the outputs or the range are listed on the right. Arrows are then drawn between the two to show which inputs correspond to which outputs. Here's an example of an arrow diagram. In this case, the input A corresponds to the output of Z, the input of B corresponds to the output of X, and the input of C corresponds to the output of Y. To determine if an arrow diagram represents a function, each input value should have exactly one arrow. In the case of this one, there's one arrow coming from A, one coming from B, and one coming from C, so this would represent a function. Here's another example of an arrow diagram that represents a function because A has one arrow, B has one arrow, and C has one arrow. Here's another arrow diagram, but this time if I look at A has 2 arrows, one that goes to X and one that goes to Z. This tells me that this particular relation is not a function. The next way we'll look at to represent functions is with tables. In the case of a table, we have an input or an X row, and then the corresponding output or Y row below that. Here's an example of a table. In this case, I can see that every number in the input row is distinct, 1, 2, 3, 4, and 5. That means that this does represent a function. If I look at this table, I can see that 2 appears twice. In addition, 1 appears twice in the input row. That tells me that this table does not represent a function since I have numbers in the input row that repeat. The next way we'll represent functions are with equations. This is one of the more commonly used ways to represent functions. And an equation will represent y as a function of x if I can write this in the form y equal to something involving only x. Some examples of these would be the equations y equal to 5 and y equal to x cubed minus 2x squared plus 8. The idea is that I should have y on one side, and the other side can involve any combination of numbers or x's. Let's consider the equation 2x squared plus 3y equal to 9. This is not of the form y equal to something, so we need to try to solve for y. The first step would be to subtract 2x squared from both sides. When I do, I end up with 3y equal to 9 minus 2x squared. The next step would be to divide each term by 3. When I do, I end up with y equal to 3 minus 2/3 x squared. Since I have this written uniquely as y equal to something involving only numbers and x's, this is a function. Next, let's consider the equation 2x plus 3y squared equal to 9. This time, if I want to solve for y, the first step would be to subtract 2x from both sides. I would then have 3y squared equal to 9 minus 2x. The next step would be to divide everything by 3. When I do that, I get y squared equal to 3 minus 2/3 x. Finally, I would take the square root of both sides, but when I do, I have to do plus or minus. And that actually causes an issue and makes this not a function. This time, I would have two answers for y rather than just a single answer. In general, anytime y is raised to an even power, 2, 4, 6, 8, etc., the equation will not represent a function. The final way we'll look at to represent a function is with a graph. To determine if a graph represents a function, we use what's called the vertical line test. The vertical line test states that if a vertical line intersects the graph more than once, then it is not the graph of a function. Let's consider this graph here. If I try to draw a vertical line no matter where I try to draw it, it's going to intersect the graph one time. That tells me that this is in fact a function. On the other hand, if I have a graph where I can draw a vertical line, such as this one here, that intersects the graph more than once, this one intersects twice, then this is not the graph of a function.